Hello again. Welcome to Einstein Helps with Grade 10 Math, and the unit is measurement. This is lesson number 5. In this lesson we will focus on 3 or 4 areas. First, we will introduce the idea of extending beyond one dimension and getting into 2 dimensions. Then we must learn how to properly label the sides of right triangles in preparation for trigonometry. Then we will introduce the 3 basic trigonometric functions. And then finally we need to learn how to solve right triangles. And we will give examples for solving a few more tricky situations. Introduction to dimensions. Up to now we have measured lengths. That is a linear measurement because it's along one line in one direction, positive or negative. Here we need to remind you what a line is in mathematics. In math, a line is per definition a straight line. In math we cannot have curved lines. In art class you can make nice curved lines. In math, every line needs to be perfectly straight. Actually, we cannot even draw a line because a line officially has no thickness at all, and it has no end points. It doesn't stop, but it goes on forever in both directions. So, in some countries and in some textbooks, they draw a line as a line segment, and instead of end points, they have little arrows at the end to suggest it continues forever in both directions. A line segment is a piece of line. It does have 2 endpoints, and therefore it does have a specific length. And then we have half lines. Half lines have only one endpoint. Sometimes we call these rays. Think about a ray from the sun. It has a beginning, but theoretically it continues forever along a straight line. But now we will talk about angles, and angles are no longer in one dimension, because typically they will consist of 2 rays going in different directions. So here we enter the area of 2-dimensional space. In one dimension, we basically have only one train track, and you can go in one direction, forward or backward, positive or negative. But now a whole new area opens up. It's a whole plane where we have parallel lines and intersecting lines, and we can have areas that are enclosed by circles or by polygons. Polygons are shapes such as rectangles and pentagons, hexagons, and of course triangles. Now remember, in linear space we measured in the metric system in meters or perhaps centimeters. But now we deal with area. We have more than one direction. And so if we calculate area, we always need 2 lengths that we multiply. You know, if you multiply a times a, you get a squared. So also, when you multiply 2 lengths, instead of centimeters, you get centimeter times centimeter equals centimeter squared, or squared centimeters. Introducing the labels of the sides in right triangles. This is important before we can define and use the basic trig functions. So you know that a triangle is a form of a polygon. So trigonometry means trigonometry, which means it's the measurement of triangles. So here we have an example of a simple triangle. Notice the names of the vertices, or the endpoints, A, B, and C. A is one vertex. The plural form is vertices. It also has three sides. And please notice that for the labels of the vertices or angles, we use capital letters, and for the labels of the sides, we use lowercase letters. Sometimes for the angles, we use small Greek letters like alpha, beta, gamma, theta, and others. So in this picture, I have a triangle with an angle alpha. It is a right triangle because one of the angles is right. That means it has a size of 90 degrees. Because it is a right triangle, it must have two right angle sides. And the right angle is enclosed between those two sides. So now we have to see how we label the sides in relationship to angle alpha. So first, one of the sides is actually part of the angle. And this side is called the adjacent side. So notice the adjacent side is always a right angle side. There is one other right angle side, but this one is not adjacent. This one is opposite from angle alpha. We call it the opposite side. And lastly, we have a side that is the longest. And this one is always across from or opposite from the right angle. This one we call with a Greek name, hypotenuse. That's a difficult word. No, it doesn't mean it's a toilet in a flying passenger jet. It is Greek. And the Greek word hypotenuse is made up of two words, hypo and teinine. Hyperactive means overactive, more active than normal. So hyper means over or above. Hypo means less or under. So this is the first part of the word hypotenuse. Teinine means stretch. So literally, hypotenuse means understretcher or understretched. The English word would be subtend, subtender or subtended. Now check the word list. You can find it under the section of resources on the website. And if you look for the word subtend, you know that this word is also used in relationship with cyclic quadrilaterals. That means four-sided shapes that fit within a circle. So now we know that at least in relationship to angle alpha, which side is adjacent, which side is opposite, and which side is the hypotenuse. Finally, here I give you a picture that hopefully will illustrate the idea of hypotenuse to help you remember it. Look here. I'm stretching my arms under a ruler. With my arms, I make an angle of about 90 degrees, and this is stretched under the hypotenuse.
Sokatoa, Sokatoa, I love you so. Your sun-kissed beaches are so wonderful.
Well, Einstein, what was that all about? Well, it's a teaching trick. Sokatoa. It sounds a bit like the tropical island of Samoa. Sokatoa is a trick that is well known by math students all over the world. Sokatoa gives all three basic rules for the trig functions, sine, cosine, and tangent. So, The sine is the opposite over the hypotenuse. Ka, the cosine is the adjacent over the hypotenuse. Toa, the tangent is the opposite over the adjacent. Let's put this into practice. Here I have a triangle ABC. What is the sine of angle A? Well, sine is opposite over hypotenuse. So it is BC over AC. That is 3/5, or 0.6. What is the cosine of A? The cosine, Ka, is adjacent over hypotenuse. So that is AB over AC. So that is 4/5, or 0.8. What is the tangent of A? The tangent of A, Toa, is opposite over adjacent, so it is 3/4, or 0.75. Of course, I can do this for angle C. Sine of C is opposite over hypotenuse, is 4/5, is 0.8. The cosine of C is adjacent over hypotenuse, is 3/5, or 0.6, and the tangent of C is opposite over adjacent, is 4/3, or 1.3 repeating. Now, as you will see, these three rules are very powerful in solving right triangles. But there are two other rules that we need to briefly review. Take a look at this triangle. Two sides are given. How can we find the size of the third? Well, you know the rule, Pythagoras. So the hypotenuse is given, so is 13 squared minus 6 squared, and then take the square root. What about this question? Here we have one angle given. Oh no, two angles are given because we have a right angle and we have an angle of 63 degrees. Here we have a rule that the three angles of a triangle must add up to 180 degrees. Since 90 is already given, we have two sharp angles, or two acute angles, that together also must be 90 degrees. One is 63, so 90 take away 63 means there is 27 degrees left for the missing value. So now we will apply this information in solving right triangles. Solving a right triangle means that you find the size of all the sides and all the angles. So some information, of course, must be provided. Okay, we will do some problem solving for trigonometry. And here's the first example that I have. Of course, it's a right triangle. As we can see, it's triangle ABC. Two bits of information are given. Beside that, there's a right angle. There's one angle of 70 degrees. So actually, we could calculate angle B already. And there's one side given. We will use trig here. And please be reminded, we're not doing any measuring anymore. Even though the unit is called measurement, we will do calculation using the formulas that we've just learned. And so we will use the trig function. So the diagram here is not really made to scale. It's not proportionate. It's just a sketch. So don't start measuring things like angles or lengths because it won't work. Well, angle A is given, so we'll start with angle A. And notice that BC is also given, and that side is opposite. If that side is opposite, that means that we can use two formulas. We can use the sine or the tangent, because the sine and the tangent both use the opposite in their formula. All right, so that's what we will do in this question. I will set it up with sine of angle A and that will be the opposite over the hypotenuse, and so it will be 8.5 divided by AB. All right, well, this is a bit tricky because now I have a fraction here, and we don't like fractions. So as I think you've learned in the introduction or exploration, we will have to multiply both sides by the denominator. So we'll multiply both sides by AB. And so what we'll get now is we'll get AB sine A equals 8.5 times AB divided by 8B, so they will cancel out. So this is my new formula, but I do know what sine A is because that is actually sine of 70 degrees. All right, so the sine of 70 degrees, I can get that from my calculator, and the sine of AB, the sine of 70 equals 0.93969, so that's a long story. We can abbreviate it to about 4 or 5 decimal places. So we get AB times, and I will write down 9396 or 7. All right, 9397 equals 8.5. So that means that AB will be divide both sides by 0.9397 is 8.5 divided by 0.9397. So I will do 8.5 divided by the previous answer, and so that means that AB is 9.0455. Of course, I will round it because this one is given in millimeters accurate, so AB I will give also in millimeters accurate. So it's actually 9.0 centimeters. All right, so now we got AB. Of course, AC I can measure with Pythagoras because I know the hypotenuse and I know the other side. But if we use trig, then in this case we will use the tangent of A, and the tangent of A is 8.5 over AC. So now we have the tangent of 70 equals 8.5 over AC. All right, and the tangent of 70 equals 2.74477. All right, so I will write 2.7475 equals 8.5 over AC. Okay, same thing. I have AC as denominator, so I multiply both sides by AC, and then I will get 2.7475 AC equals AC cancel out is 8.5. Divide both sides by 2.7475, and I will get AC is 8.5 divided by 2.7475. And I do 8.5 divided by the previous answer, and I would get AC equals 3.09375, which is rounded off 3.1 centimeters. Make sure you get your units in place. And now there's only one thing left, and that's angle B. And so angle B has to be 90 minus 70 degrees, and so will be 20 degrees. So that all three angles together are 180 degrees. So that's your final answer. Now we know the three angles and the three sides, so it is solved. We go to problem number 2. And in problem number 2, we have a similar situation. We have a right triangle. And in this case, the hypotenuse is given and one of the angles is given. I can again calculate the other angle. All right, actually we could start with that. Angle F is 90 minus 55 is 35 degrees. All right, well, let's start with this angle now. We have the hypotenuse, so there's two things we can use. We can use the sine and the cosine. And that's good because with sine I get EF and with the cosine I get DE. So we'll set both of them. The sine of 55 equals EF, that's the opposite of D, over 15, that's the hypotenuse. And the cosine of 55 is the adjacent, that is DE, over the hypotenuse, which is 15 centimeters. The units will come later. So the sine of 55 equals 0.819. 2 equals EF over 15. All right, so multiply both sides by 15. That's the denominator here. And I get EF equals 15 times 0.8192. So I leave this in the memory here and I go times 15 equals, and I get EF is 12.2872 or 3. And so round it off EF, round to 1 decimal point, and I get 12.3 centimeters. Does that make sense? EF, this one is 15, this one 12.3. That does seem to make sense. Go on here with cosine of 55. The cosine of 55 equals is 0.57358 equals dE over 15. Multiply both sides by 15. That will get rid of the denominator and therefore also the fraction. So then these cancel out and I get 15 times 0.57358 equals dE. And so dE is 15, this times 15. And so I will get 8.6. dE is 8.6036. etc. And so if I round that off, I get dE is 8.6 centimeter. All right, we already got what angle F is. So now we got all three angles and we got all three sides. That is problem number 2. Now a different style of question, because in this case no angle is given except for the right angle, but 2 sides are given. All right, which sides are given? Well, it's the right angle side. So I can use the tangent of M or the tangent of L. The tangent of M is opposite over adjacent, is 15 over 5, is 3. And the tangent of L is 5 over 15, is 1/3 or 0.3 repeating. Well, that's easy because now I can just go back, and here in this case I go second tangent to tan to the power minus 1, 3 equals, and so that's angle M. Angle M is 71.565, so angle M equals 71.6 degrees. And here we get tangent L is 0.3 repeating, so I go here second function tangent, and I go 1 divided by 3 equals, and here I get L equals 18.4349, and so rounded off I get L equals 18.4 degrees. And then, well, there's one more side, and I can use sine or cosine, or I can use, in this case, I could use Pythagoras. So Pythagoras, unless the question specifies that I have to use trig, I would use Pythagoras. Okay, so ML is the square root of 5 squared plus 15 squared. Okay, so ML is the root of 25 plus 225. So ML is the root of 250, and the root of 250 equals 5 square root of 10. So that's actually ML is approximately 15.8 centimeters. All right, that is question number 4. Well, this lesson is longer than it should be because of the explanations of the 3 trig problems. So the rest of the trig problems, I will put workouts on paper as a special attachment. You can check it out there. But please review this several times if you don't get it right away, and use the pause button to slow it down, to check out step by step, and then see if you can do it by yourself. The exercises will have a few more challenging questions as well. But with lesson number 6, I will also provide the workouts for those. So good luck, and make sure you practice a lot. See you later.